Welcome to Module 6. We've written contracts, we've tested them, and we've deployed them. But there's something that separates contracts that work from contracts that are safe. This module is about security. Not advanced security, not obscure attacks, just the fundamentals. Because smart contract bugs aren't inconveniences, they're catastrophes. By the end of this module, you'll understand the most common vulnerabilities, how to prevent them, and the mindset that keeps your users' money safe. Let's build secure contracts. I want to start by showing you why security in smart contracts is different from other kind of programming. In traditional software, your web app, your backend, and your database, you deploy code, a bug is discovered, you panic a little, then you fix the code and you redeploy. Downtime? Maybe an hour. Are users annoyed? Probably. But the problem is solved and you can patch production. You have a kill switch, you have a rollback, and you have hotfix capability. On Ethereum, you deploy code to the blockchain, bytecode is stored at an address, and that code is immutable. A bug is discovered, and you realize immediately there's no patch. You can't SSH into Ethereum. You can't hotfix production. You can't delete the database and restore from backup. That code runs exactly as written forever. If there's a vulnerability, it exists permanently. If funds can be stolen, they will be stolen. In Web 2, bugs are recoverable. In Ethereum, bugs are permanent. This is why security is not optional. It's foundational. Because code is immutable, you need a different mindset about security. On Ethereum, code deployed is code forever. No SSH access to servers, no hotfix capability, no database rollback, and no undo button. Everything is permanent. Here's the most important principle in smart contract development. Ethereum does exactly what you tell it, not what you mean. If you write a function that sends ETH to anyone who asks, Ethereum will send ETH to anyone who asks. It doesn't care about your intent. It executes the code. This means we always need to assume worst case scenarios. Assume users will find bugs, and assume attackers will try to exploit your code. We need to test thoroughly before deploying. This is the only chance to catch bugs. We need to use security patterns and follow proven patterns that prevent common mistakes. And we need to validate all inputs. Never trust that users will call your functions correctly. Professional developers think differently. They ask themselves, what if someone sends 0? What if someone sends the maximum value? What if they call this function 1,000 times in a row? What if they call this function from another contract? What if they call function B before function A? You must anticipate every edge case and every misuse and every attack. Because once the code is deployed, you cannot fix it. This defensive thinking becomes second nature. Embrace it now. Let me introduce the most famous smart contract vulnerability, reentrancy. Imagine you're at an ATM. You request $100. The machine dispenses the cash and hands it to you. Then it updates your balance, deducting the $100. That's the normal flow. Dispense, then update. But what if, and this is the key, what if you could somehow interrupt the process after step 1 and before step 2? After you have the cash, but before your balance is updated. You could request the money again. The ATM checks your balance, it's still $1,000, and hands you another $100. You could keep interrupting, draining the machine completely. That is reentrancy. Exactly that pattern. Reentrancy occurs when a smart contract sends ETH or calls another contract. That external address calls back into the original contract before the first call finishes executing. Because Ethereum allows contracts to call other contracts, execution can jump back into your contract unexpectedly. Ethereum is different from traditional systems. Contracts can call each other. When contract A calls contract B, control shifts to B. B can call A back. A can call B again. Execution is recursive. If you're not careful, this nesting can create vulnerabilities. Reentrancy is the most famous vulnerability because it's real, devastating, and surprisingly easy to miss. Here is a vulnerable vault contract. Let me highlight the critical issue. This withdraw function checks the balance of the user, sends ETH to the caller, and reduces the balance. Notice the order. Steps 2 and 3 are in the wrong sequence. When message.sender.call is executed, control passes to the caller's code. If the caller is a contract, that contract's fallback function runs. The fallback function can call withdraw again. At this point, what's the caller's balance? It hasn't been updated yet. So the contract thinks the caller still has the full balance and allows another withdrawal. This repeats and funds drain. The execution path is as follows. The attacker calls withdraw for 100. The balance check passes and the attacker has 1000 ETH. The contract sends 100 ETH to the attacker. The attacker's fallback receives the ETH and calls withdraw for 100 again. The balance hasn't been updated yet, still 1000 ETH. The check passes again. Contract sends another 100 ETH. This repeats hundreds of times and the contract is drained. This vulnerable pattern, external call before state update, is the classic reentrancy bug. Now let's look at how to fix it. The fix is simple, but it's a pattern you'll use in every single contract you write. It's called the checks, effects, interactions pattern, or CEI pattern. Checks first verify conditions. It can check that the caller has enough balance. Effects update state. This reduces the balance immediately. Then interactions. These call external contracts. Only after state is updated, send the ETH. If reentrancy happens now, it doesn't matter. When the attacker calls withdraw again, the check executes and verifies, does the attacker have $1,000? No, they now have 900. We already deducted. The check fails, insufficient balance, the call reverts, and reentrancy is prevented. The balance update before control passes to external code. If external code calls back, it sees the updated state. The attacker can't exploit what's already changed. CEI is so fundamental that it becomes habit. Every external call should be the last thing in a function. Get this pattern right and you prevent an entire class of vulnerabilities. CEI is your weapon against reentrancy. You need to master it. Here's the fixed version of the contract using the CEI pattern. The difference compared to the previous contract, one line is moved. That is the difference between safe and catastrophic. Now another critical security pattern, access control. Many functions should only be callable by specific people, the owner, admins, and approved addresses. Without access control, anyone can call anything. That's a disaster. In this contract, anyone can call set funds. They can set total funds to 0 or to 1. There's no restriction. The solution is modifiers. Solidity has a feature called modifiers. They're like middleware, code that runs before a function. Let me break this down. Here we have a contract with a constructor function. This runs once at deployment. It sets the owner to whoever deployed the contract. Then we have an only owner modifier. This checks is the caller the owner, and if not, revert with an error. After that, the underscore means run the function body here. By adding the only owner modifier to the set funds function, we restrict access. Only the owner can call set funds. If anyone else tries, the required check fails. Access control is foundational. Many hacks happen because critical functions lack access control. Developers forget to add the modifier or they add it to the wrong function. Every admin function, pause, set owner, withdraw must have access control. Modifiers are your tool for enforcing permissions. Use them everywhere admin functions exist. Integer overflow and underflow. This one is simpler because modern Solidity protects you, but you need to understand what changed and why. Before 0.8, integers would silently overflow or underflow. That means that if we had a uint8 set to the number 255 and we added 1 to it, it would wrap all the way around back to 0. This is called overflow. Similar for underflow. If we had a uint8 of 0 and we subtracted 1, it will wrap all the way around to 255. These silent wraps caused serious bugs. Attackers exploited them mercilessly. Solidity 0.8 introduced checked arithmetic by default. Instead of silently wrapping, a transaction would revert. This is much safer. Let me highlight some common mistakes that beginners often make. The one is sending ETH before updating state. Second, not considering callback behavior. If developers forget that call can trigger fallback functions can call you back. Always assume external calls might re-enter. Then, access control mistakes. Forgetting modifiers on admin functions. Trusting the front-end validation. Front-end code validates inputs, but Ethereum doesn't run on your front end. Users can call contracts directly. Thus, we always need to validate inputs on the contract. Assuming user honesty. Users will try to exploit your contract. Don't assume they'll use it correctly. Never assume Ethereum is like other systems. It is not. Contracts can call each other. Execution is recursive. Always assume the worst case. Always test edge cases. What happens with zero input, maximum input, negative values? We always need to test them. Avoid these mistakes and you'll prevent most vulnerabilities. Before you deploy to mainnet, run through this checklist every time. Are all admin functions restricted? Is state updated before external calls? Are all inputs validated? Are edge cases tested? Is there reentrancy protection in place? Are gas limits considered? And are events emitted for tracking? Each item addresses a real vulnerability class. Admin restrictions prevent unauthorized access. State updates prevent reentrancy. Input validation prevents logic exploits. And edge case testing prevents boundary bugs. Reentrancy protection prevents recursive calls. Gas awareness prevents out of gas reverts. And events allow for off-chain tracking. Once deployed, you cannot change this. You cannot add a missing require. You cannot reorder operations. Run through this checklist every time and make it a habit. This checklist is your last line of defense before going live. Let me summarize the security patterns you will use constantly. Pattern 1. Checks effects interactions. The order matters. Checks first, interactions last. Pattern 2. Access control with modifiers. Restrict who can call all critical functions. Pattern 3. Input validation. Never trust user input. Validate everything. Pattern 4 is event emission. Emit events so off-chain systems can stay in sync. Pattern 5 is the pull pattern, not push. Instead of sending funds to users automatically, we let users pool their own funds. This is much safer. With a push pattern, you control who receives funds. You must call everyone. It becomes complex. With a pull pattern, each user controls their own withdrawal. It's simpler and safer. These 5 patterns are your foundation. Learn them, use them, as they prevent most vulnerabilities. I want to return to the fundamental reality that drives all of this. Immutability changes everything. On Ethereum, if you have a bug, you cannot fix it. It is permanent. There is no second chance and there is no hotfix. The code at that address is what runs forever. If that code has a bug, funds can be stolen. They will be stolen. This isn't theoretical. In 2020, a contract called Harvest Finance lost 50 million to a flash loan attack. In 2021, Poly Network lost 611 million to a reentrancy-like exploit. So what this means is that testing isn't optional, code review isn't optional, and security thinking isn't optional at all. You must assume you will have made a mistake. You must test to find it before deployment. Even professional auditors miss vulnerabilities sometimes. That's why they exist. Security audits. You hire experts to review code before mainnet deployment because mistakes are expensive. Immutability means consequences are permanent. This drives everything we've discussed in this module. Here's a quick exercise to apply everything we've learned. In this exercise, build a vault contract that accepts deposits from users, allows users to withdraw their funds, prevents reentrancy attacks, and restricts emergency pause to only the owner. Key concepts to apply are use of the CEI pattern, access control using modifiers, input validation, and state management with emitted events. You've now learned the fundamentals of smart contract security. Immutability means no hotfixes. Code deployed is code forever. Reentrancy is a critical vulnerability where external calls trigger recursive execution. The checks effects interactions pattern prevents reentrancy by updating state before external calls. Access control via modifiers restricts who can call critical functions. Solidity 0.8 and greater prevents integer overflow underflow by default. Testing before deployment is your only defense. Professional developers think defensively. They always assume users will try to exploit the contract, external calls will re-enter, inputs might be invalid, and worst case scenarios will always happen. This paranoid mindset prevents bugs. Always remember this. Ethereum does exactly what you tell it, not what you meant. If you write vulnerable code, Ethereum executes it vulnerably. There is no safety net. There is no second chance. Only your code quality stands between users' funds and disaster. You now understand the fundamental security principles. As you build more complex contracts, you will encounter more sophisticated vulnerabilities. But the foundations are here. Immutability, reentrancy, access control, and state management. Master these and you can build secure contracts. Smart contract security is not a side topic. It's the foundation of everything. Great work completing Module 6. You're now starting to think like a security-conscious developer. Your users' trust and their funds depend on this thinking.